last class we started discussing the problem of structure formation in the universe. If you look at the universe around us, you find structures on scales extending possibly all the way up to 100 megaparsec. But there is evidence that the universe much earlier on was very close to homogeneous and isotropic. So the problem is, how do the structures that we see in the present day universe emerge from a universe that was, to start with, very close to isotropy and homogeneity. And the basic picture that we have, which I mentioned in the last class, is that early in the universe there were some very small fluctuations which grow by the process of gravitational instability to give you the structures that you see now. So after having told you this, we were going into the mathematics, trying to work out if such a thing is really possible. So we are describing the constituents of the universe as a fluid, and this fluid is governed by the following fluid equations. We have first the continuity equation. This arises from the conservation, local conservation of mass. The matter does not get created or destroyed locally. So if the density changes, there has to be an accompanying flow in the mass. This is the mass current. Then we have the conservation of momentum, which gives rise to the Euler equation. So we have the convective, this is the convective derivative of the velocity. This is equal to the minus the pressure gradient divided by the density and the gravitational acceleration. The gravitational acceleration, the gravitational force here has been represented by a potential, and this potential satisfies the Poisson equation. Del square phi is 4 pi g rho. So these were the three equations which govern the motion, the evolution of a fluid, and this fluid, we believe in our picture, fills the entire universe. Now with this model, we started off with a simple kind of analysis. So in this analysis, there is no expansion. We have done away with the expansion of the universe, and we consider a homogeneous uniform fluid. And this fluid starts off with a static configuration. So the density initially is just a constant rho bar. The velocity, which I represent by u, the fluid velocity, is initially 0. The pressure is initially a constant p bar. The potential is initially 0, and we put small perturbations, delta rho, the perturbation in density. So the density is now not a constant, but it has some small fluctuations which vary from place to place. There is a small velocity v, which has now also been introduced. So the fluid now is no longer static at rest, neither is it static. It has a velocity which is also possibly time dependent. Then there are small fluctuations in the pressure, which again are a function of r and t, and there is a change in the potential, a small fluctuation in the potential, also psi, and all of these small fluctuations, delta rho, v, delta p and psi, are of the order of a small number epsilon. So let me just remind you that we have written this, instead of v, we are using the symbol u for the fluid velocity, and u we have represented as 0, which is the undisturbed condition, and there is a small disturbance v. Rest of this I think is clear. So what we do now is we take these and put them in these equations. So if you take the continuity equation, the mean density is a constant, so you have an equation for the density fluctuation, the time derivative of this plus the divergence of rho plus u, rho into u, this is equal to 0. Now here you have one term rho into 0 which cancels out, you have another term rho bar into v which is of order epsilon, there is another term delta rho into v which is of order epsilon square, delta rho into v is of order epsilon square. Now here we have two terms, one of order epsilon, the other of order epsilon square. We are assuming that epsilon is a small number, all these fluctuations are extremely small, characterized by this small number epsilon. So, a quantity of order epsilon square is much smaller than this. So, all nonlinear quantities are assumed to be small, whereby we can linearize this equation, and we have this equation del the time derivative of the density fluctuation plus rho bar into the divergence of the small velocity fluctuation is equal to 0. This is the linear continuity equation. Similarly, let us linearize the Euler equation. Here this term is linear, this term is going to be non-linear, so we can drop this. Here the mean pressure has no gradient, so it is only the pressure fluctuation that comes in the numerator. The denominator has rho bar plus delta rho, but the term involving delta rho will give rise to a second order term which we drop. So, the linearized Euler equation, let me write down the linear equations. The linear equations are the time derivative of delta rho plus rho bar, the divergence of V. This is equal to 0. This is the continuity equation. Next, the linearized Euler equation, del V del T is equal to minus grad delta P by rho bar, and there is a term minus grad psi, the fluctuation in the gravitational potential, and we have the Poisson equation del square psi. So, this is the fluctuation in the potential. This arises only because of the fluctuation in the matter. So, we have these three equations, and we would now try to solve these equations together. So, the way to proceed is to first take divergence of this equation. So, when you take the divergence of this equation, what you get is and the divergence of V is the time derivative of delta rho divided by rho bar. So, this term can be written as 1 by rho bar with a minus sign. You will get a minus sign when you write this. So, this is equal to minus this divided by rho bar. So, what you have is the second derivative this is equal to minus del square delta P by rho bar, and we can use the Poisson equation to eliminate psi. So, we have del square of psi, which is 4 pi. So, what you have here is minus 4 pi g delta rho. So, that is the equation which you get. Now, this equation involves two different things. One is the density fluctuation and other is the pressure fluctuation. Now, consider a gas. In that gas, if I compress it, the pressure there is going to go up. If I expand it, rarefy it, the pressure there is going to go down. So, in most situations we can get a relation between the pressure and the density, and we can write delta P as a function of delta rho and we shall use the symbol Cs square to denote this. So, Cs square denotes this derivative del p del rho. For the reason why we shall use this symbol Cs square to denote this shall become clear shortly. So, with this we can write this equation as, we can drop the minus sign, take the rho bar and multiply it throughout. What we get finally is so that's the equation governing delta rho, which we finally obtain having used the symbol Cs square to denote the partial derivative of p with respect to rho. So, this is the equation. Before going any further, let me explain to you how we can calculate delta, the partial derivative of p with respect to rho. So, we have a gas, let us consider a monoatomic gas as our specific monoatomic gas. This exercise could be done for any medium. Let me just do it as an example for monoatomic gas. So, I have a monoatomic gas, this is my fluid, let me just draw it like this, which is uniform, and then I have compressed a certain part of the fluid or rarefied it. So, this is a part of the fluid and I have either say compressed it or rarefied it. So, I have compressed it, let us say, and maybe I have also rarefied this part. So, I have made its volume, taken a certain volume and made it larger. Now, we are going to assume that these disturbances in the fluid are adiabatic. So, we have put an adiabatic disturbance. Let us just try to understand why the justification for such an assumption. What is the justification for assuming that it is an adiabatic compression or rarefaction? What do we mean by a compression or rarefaction being adiabatic? Let us just ask that question. If I take a gas and compress it, the temperature of the gas is going to go up. Similarly, if I take a gas and expand it, rarefy it, its temperature is going to go down. Now, inside this gas, this fluid that fills our universe, there will be, if there is a disturbance, it essentially means there are rarefactions and compressions. And a rarefaction can increase the temperature, a compression can decrease the temperature. Now, there will be a time scale for these rarefactions and compressions to occur. If the time scale is much fast, so suppose I compress this part, it will get heated. Now, the heat generated here, the temperature here is higher than the temperature outside, so there may be a flow of heat from inside to outside. But if the rarefaction and compression occur on a time scale much smaller than the time scale required for the heat to flow, then we can ignore the flow of heat and treat this as an adiabatic process, which is the situation over here. So, we are going to assume that even if you compress the fluid or rarefy this gas or rarefy it, the temperature goes up and down, but there is no flow of heat. So, we have a gas, and if there is no flow of heat, if it is adiabatic, then we can write down the first law of thermodynamics, the internal energy du plus P dV, this is equal to 0. We also know that for an ideal monoatomic gas, the internal energy U is N K Boltzmann into T, where N is the number of atoms in the gas, Kb is the Boltzmann constant, and T is the temperature, U is the internal energy. So, there is some mass of gas which we are dealing with, that is our system, its internal energy is given by this. And we know that a monoatomic ideal gas, this will have 3 by 2 here. If it's a monoatomic gas, each degree of freedom, each translational degree of freedom has half kT, and there are 3 of them, so it is 3 by 2. We also know that it has an equation of state PV is equal to N kB T. So with these two things, we can write the internal energy, the du. So this kB, N kBT we can write as P into V. So we can write this du as d of 3 by 2 PV. And we have another term P dV, this is equal to 0. So now if you break this up, you will get one term which is 3 by 2 P dV, and you combine with this P dV, that will give us 5 by 2 P dV plus 3 by 2 V dP is equal to 0. Now what you do is very straightforward. You divide this whole thing by P into V, and what you have is 5 by 3. So I am dividing this with this 2 in the denominator can be done away with. I divide this by P into V, so P cancels out. What I have is dV by V which implies that the derivative of ln V to the power 5 by 3 into P, this is 0. If I differentiate the V term, I will get this. If I differentiate the P term, I will get this. So this derivative is 0, which implies that P V to the power 5 by 3 is a constant. This is called the adiabatic index. So in general, we can write it as P V to the power gamma is a constant, where gamma is Cp by Cv, the specific heat capacity at constant pressure by the specific heat capacity at constant volume. This is called the adiabatic index gamma. We have worked it out explicitly for a monoatomic gas. So P into V to the power gamma is a constant, where gamma is an adiabatic for a adiabatic process, which you can write in terms of the density as P rho to the power minus gamma equal to constant C. C is a constant, not the speed of light here, which allows us to calculate del P del rho for an adiabatic process. So all that here you have to do is differentiate this. So you have del P del rho into rho to the power minus gamma into minus P into, so I have P and then I have minus gamma, so this gamma can come here, minus gamma. If I differentiate this, I will get minus gamma P rho, and I will have to, I have minus 1 minus gamma. This is equal to 0. So we can take this onto the right hand side and get rid of this rho to the power minus gamma throughout. So what you have left is del P del rho is equal to gamma P by rho. And for a monoatomic, this is in general, where gamma is the adiabatic index, P by rho is the ratio of the pressure to density. For the adiabatic gas, For this monoatomic gas, we know that PV is equal to N kBT. So you can write this for a monoatomic gas. Let me just do it explicitly. For a monoatomic gas, P is equal to N kBT by V, and N into the mass of each atom divided by V is the density. N is the number of atoms. So N into the mass of each atom is the divided by V is the density, that is the volume. So this will become P is equal to rho kBT by the mass of each atom if it is a monoatomic gas. So this ratio becomes equal to gamma kBT by the mass of each atom. That is the number Cs square, which you can calculate, which I have calculated explicitly for perturbations in a monatomic gas. Okay. So you can estimate this number easily if you know the temperature of the gas. For a monatomic gas, it only depends on the temperature, nothing else. Okay, there is no dependence on the density or anything else. Fine. So let us go back to the equation that we are dealing with. So this is the equation, and we know how to calculate this Cs square, and now we have a partial differential equation for delta rho, the density fluctuation. For a monatomic gas, this is just gamma into kBT by the mass of the atom. Fine. Now we want to solve this equation. The way we proceed to solve this equation is that we take a trial solution, a plane wave trial solution, delta rho, function of R and T. Let me take a plane wave trial solution, which is A e to the power. We will take, for simplicity, a wave only along the x axis, so I kx minus omega t. We could have written it as k dot r, but for simplicity I have just took it like this. So we take a trial solution that looks like this. This is a plane wave solution. All of us are familiar with this. Now if you put this solution over here, if you differentiate this twice with respect to time, you pick up a factor of minus omega square. Every time you differentiate it with time, you pick up a factor of minus I omega. So what you have here is minus I omega square delta rho, this is the first term, is equal to Cs square. If I differentiate it with respect to x, the y and z derivatives don't count twice, then I pick up a factor of I k square into I k square delta rho plus 4 pi g rho bar delta rho. So this here you can calculate, you can subtract out delta rho throughout, and what you get is this will give you minus omega square is equal to minus k square plus 4 pi g rho bar. So you are led to a dispersion relation. Let me write down the dispersion relation. Omega square is equal to Cs square k square minus 4 pi g rho bar. So we are looking for solutions to this partial differential equation, and we have taken a trial solution which is a plane wave like this, and we have now obtained the dispersion relation for this plane wave. So this is the dispersion relation for this equation. By dispersion relation, this is the dispersion relation. A dispersion relation refers to a relation between omega, the angular frequency, and k, the wave number. and here we have obtained the dispersion relation. Now let us spend a little while understanding what this dispersion relation tells us. The first point to note here is that there is a particular wave number called the Jeans. This analysis was first done by Sir James Jeans. So there is a particular number called the Jeans wave number. This is called Kj, denoted by J, which has a value. So Kj has the property that for this value of the wave number K, the angular frequency is 0. So Kj has the value square root of 4 pi g rho bar divided by Cs square. That's the Jeans. This is called the Jeans wave number or Jeans mode. So if K has a value equal to this Jeans wave number, if the wave number K of the trial solution that you have taken has a value equal to this, then the angular frequency is 0. This is a solution that doesn't have any time dependence at all. If the angular frequency is 0, the time dependence vanishes. Okay. Now let us first consider K, a wave with wave number K much greater than the Jeans wave number. So in this situation, when K is much greater than the Jeans wave number, you can actually ignore this term is much larger than this. The two are equal when K is exactly equal to Kj. If K is much larger than Kj, this term dominates, so we can ignore this term, and we have omega is equal to Cs K. So this is the dispersion relation that you have for wave numbers which are much larger than the Jeans wave number. Writing this in terms, let me write this in terms of the wavelength. So there is equivalently a wavelength associated with every wave number. So the wavelength is 2 pi by K. So there is also a Jeans wavelength lambda j, which is 2 pi by, this is the Jeans wavelength. So these are disturbances which have a very small wavelength. So the Jeans wave number has a certain wavelength, and the disturbance, this is the lambda j, and the disturbance that we are talking about is much smaller than this. So these are disturbances which are smaller than the Jeans wave number, smaller length scale, and such disturbances have a dispersion relation that looks like this. This is very familiar, right? So what is the phenomena that is occurring over here? Essentially, you can ignore this term. For large K, you can ignore this term. This is the self gravity, you can ignore it. So this, without this term, this is just the wave equation, and this Cs square is the speed, the phase velocity of the wave. This Cs square is the phase velocity omega by K. Now what kind of a wave is this? What kind of a wave? We know that if you have a gas, some fluid, if you put an adiabatic compression and leave it, some adiabatic disturbance and leave it, then it will oscillate, and these oscillations are these sound acoustic waves or sound waves. So what you have here is nothing but a sound wave. So these are sound waves, acoustic wave or sound wave. So in this gas you have produced sound waves. So you have an interplay of two things, and if you compress the gas in one place, so here you have, this shows you the delta rho In some places you have compressed the gas, and in other places you have rarefied the gas. In the places where you have compressed the gas, you have pushed a gas that is this big into a smaller volume. Gas that is this big has been pushed into a smaller volume. A pressure gradient develops, so the pressure inside is more than the pressure outside. What it does is it pushes it out. Now, the part outside, if this gets pushed out, the region outside will now get compressed, and that will again push it in. So you have this interplay, and you have a disturbance that propagates, because when you put back, if you have this is a traveling wave solution, so you have a disturbance that propagates. So with time, this wave, I have a wave like this. With time, after some time, the disturbance would have moved forward. It will look like this. So the point where you had a maxima has now shifted here, and later on it would have shifted further. If you look at one fixed position, the amplitude just oscillates up and down, e to the power I omega t. So this is the sound wave, the familiar sound wave by which sound propagates through our atmosphere, for example. Okay, so if in a gas, if you put fluctuations that are very small, smaller than the Jeans length scale, what you do is you generate sound waves. The amplitude keeps on oscillating with time, and you cannot produce large scale structures with such disturbances. They don't grow, the amplitude just oscillates. Okay. Let us now consider the other possibility. The other possibility is where the wave number that you are dealing with is smaller. So we were now looking at the wave number being larger, much larger. So let us now consider the other limit, where the wave number that you are dealing with, k, is much smaller than the Jeans wave number, or the wavelength that you are dealing with is much larger than the Jeans wave number. Similarly here, the wavelength that you are dealing with is much smaller than the Jeans wavelength. That they are inversely related, wave number and wavelength. So these are fluctuations which the wave number is much smaller than the Jeans wavelength, the wavelength is much larger than the Jeans wavelength. So if this is the Jeans wavelength, the fluctuations that we are dealing with are much larger. So they look something like this. So I am plotting delta rho as a function of x, and this is x. Okay, this x will pass through the middle x here, and these are fluctuations which are much larger in length scale. Now here, let us go back to our dispersion relation. Here, you can ignore this term. K is extremely small compared to this. So you can ignore this term, and what you get is that omega square is negative, which tells us that omega is imaginary. So what you have is omega is equal to plus minus I square root of 4 pi g rho bar. So omega, you only have imaginary solutions for such modes, such wave numbers. What does an imaginary solution imply? So this was the trial solution, and if omega is imaginary, what you see is that the solution delta rho now looks like this. Delta rho as a function of x and t is equal to, so there is e to the power I kx, this is fixed, and I have two possibilities, plus omega and minus omega. So you have a1 e to the power, you have I already here, so when you multiply it with the I over here, you will get a minus sign. So you have two possibilities. One is e to the power square root of 4 pi g rho bar t plus a2 e to the power minus square root of 4 pi g rho bar t. So now you see that you have two different solutions possible. Earlier also you had two different solutions possible. One was sine, other is cosine, we all know that. Here again you have two different solutions possible. One of them increases exponentially with time, the other one decreases exponentially with time. So if you put a perturbation, the amplitude of that perturbation can be broken up into two parts, one which will decay away, the other will expand, will increase exponentially with time. And this is what is called an instability. So you have a small perturbation, if its amplitude grows, this is what is called an instability, and this is called the Jeans instability. And you can produce structures through the Jeans instability. This is the gravitational instability. So the wave numbers which oscillate, whose amplitude oscillates, doesn't grow, they cannot give rise to structure formation. That growth cannot give rise to structure formation. The amplitude doesn't increase. You put a small perturbation, it remains small. Its amplitude only oscillates. Whereas wave numbers where there is an instability, where the amplitude grows exponentially, you put a small perturbation, after some time it would have grown. Such perturbations have the possibility of producing the large scale structures that you see now. So it is through this Jeans instability that structures are believed to have formed. So let us go into a little more detail of this. Now what is going to happen in this Jeans instability? Let me just draw a picture first and explain it to you. So we have this delta rho as a function of x, and initially it is extremely small. By our assumption, we have put a small perturbation. This is the initial one, say at time t1. After some time, what's going to happen is that its amplitude is going to grow. So this is going to become like this. It's going to become like this after some time. At some time t2, its amplitude would have increased. Now this process cannot happen indefinitely. The value of delta rho, this is the mean value 0, so it is negative on this side, it is positive on this side. Here this is an overdensity, this is an underdensity. The underdense density in the underdense region cannot cross minus rho bar, because the total density, remember, rho is equal to rho bar plus delta rho, and rho can never be negative. So delta rho can never cross, so it can keep on increasing. There is no limit to the increase of the positive side, but the negative side cannot decrease below this. The positive values can keep on increasing further and further. So this whole analysis essentially breaks down when delta rho is by rho bar is of the order unity. We have assumed to start with that delta rho is a small number of order epsilon. So this analysis is only valid when the density fluctuations are small. In the region of instability, what happens is that the density fluctuations grow with time. Once the density fluctuations grow, the analysis, this assumption that delta rho is extremely small is no longer valid after it has grown. So the nonlinear terms become important, and the whole analysis that we have done breaks down. But the main findings of these analysis are still valid. It tells us that, what it tells us is that large scale, there is a length scale called the Jeans length scale. Perturbations larger than that can, on length scales larger than that, can grow by the process of gravitational instability. The perturbations on length scales smaller than that do not grow, they oscillate. The amplitude of such perturbations oscillate. Now there is one concept, one or two concepts which I should introduce before we end our discussion of this Jeans instability. Let us consider pictorially what happens. So this is delta rho, this is x, and this is what the perturbation of a certain mode, certain value perturbation with a certain value of k looks like. Now this is an overdense region, this is an underdense region, overdense, underdense. So what is going to happen is that the density fluctuation here is going to grow, the density fluctuation here is going to, the density here is going to approach 0. The density here is going to increase, which essentially means that the matter in this region, between here and here, gets attracted and collapses over here. Similarly, the matter in this, within this, collapses here. Now, let us just take a hypothetical situation where we have, say, a gas cloud, a uniform gas cloud. In this cloud, we have perturbations of all length scale, all possible length scale fluctuations. Now, what we have seen from our analysis is that the small fluctuations, the amplitude, they do not give rise to an instability. The large amplitude, the large wave, the large length scale perturbations, their amplitude grows. Now, what's going to happen because of this growth is that there is going to be gravitational collapse in a gas cloud, for example. We are here considering a gas cloud in a galaxy. We are studying the fragmentation of a gas cloud. We know that stars are formed by the fragmentation of gas clouds. So you can apply the genes analysis to study this also. Take a gas cloud. There will be some disturbances in the density of the gas cloud. It will not be uniform everywhere, caused by whatever reason, external disturbances, etc. And we are assuming that these disturbances are of all possible wave numbers. And what we have seen is that the disturbances of small wave numbers with wave numbers k less than kj, only these disturbances grow. So these disturbances will grow, and the material, the fluctuations are going to grow, and finally it's going to lead to the collapse of material. The material, so this is one of the disturbances that grows. So the material within this region is going to collapse over to this overdense region. The material in this region is going to collapse to this overdense region, and so forth. And the smallest wavelength fluctuation that collapses is lambda j. Okay, so when this collapses, the mass that is there in this collapsed object is going to be 4/3 pi into the radius. The radius is the distance from here to here, which is lambda by 2 cube into rho bar. That's the mass. Now let us ask the question, when I have the fragmentation of such a gas cloud, what is the smallest mass object that is going to be formed? Very small wavelength fluctuations don't collapse. The smallest wavelength fluctuation that collapses is essentially the gene's wavelength lambda j. And larger wavelength fluctuations are also going to collapse. So the smallest wavelength fluctuation that collapses is lambda j, the gene's wavelength, and the mass we have seen of the collapsed object is proportional to the wavelength cube. So the smallest mass fragment that is going to form is called the gene's mass. This is the mass corresponding to the gene's length scale, mass of the collapsed object. And this is the smallest fragment. Say we are going to form stars. So this is going to be the smallest mass of the mass of the small. I mean, you're not going to produce stars of smaller mass, smaller than this, by this gravitational instability. Okay, if you find that presence of a mass smaller than this, it would have been formed by some other process. Maybe a star formed and it somehow fragmented into two parts afterwards. Okay, so this gives the gene's mass gives an estimate of the smallest collapsed mass in a certain cloud or in a certain medium. Finally, before ending today, let me give you a physical picture of where this gene's length scale comes from. So let us consider a medium over here. This is a medium. In this medium, I have put an overdensity. So the density of this region is more than the density of the region outside, and this has a length scale L. Now, in the absence of any other force other than gravity, if I have an overdense region, if I have some matter, forget about overdense, if I have some matter like this of a length scale L, this is going to essentially collapse due to its gravitational attraction in the absence of any other force. and it can be easily calculated that the time scale required for this gravitational collapse is of the order of 1 by square root of g rho. This is the time scale for free gravitational collapse. It is straightforward to estimate this. And you find this combination 1 by square root of g rho appearing in the cosmological time scales also. Okay. So you can just take a set of particles, a mass distribution, a sphere like this at rest. I leave it. So write down the equation of motion of a test particle here. Ask the question, what time will it reach the center? Okay, and it turns out that the time it takes, which is also the time for this to collapse, is 1 by square root of g rho. So if I have a mass over density, the time it takes to collapse is 1 by square root of g rho. Now, here in the gas that we are dealing with, in addition to gravity, there are also pressure. So if I have an over density over here, there will be a pressure gradient which will develop to push it out. So it's trying to collapse, and the pressure gradient develops, the pressure inside is more, which will try to push it out. Now, if I put an over density here of length scale L, the information that there is an over density of length scale L coherent, that the pressure should act coherently on this length scale and push it out, that will take a time Ts, which is the length divided by the speed of sound, to cross this. So if I put an overdense region, the pressure gradient cannot act on a time scale which is smaller than this to prevent it from collapsing. Okay. Now, if the time scale for collapse is smaller than the time scale for the sound information to cross this, if the time scale for collapse is smaller, so the collapse will occur before the sound information can cross it, then this overdense region is going to collapse. Whereas if the time scale for collapse, the time that it requires to collapse is larger, it takes a long time to collapse. The sound speed can travel from here, sound information can travel from here to here before that. So the time, the sound time is less than the time it takes to collapse. In that case, the pressure gradient will build up before the whole thing collapses, and it will prevent the collapse. So here it oscillates. So you have these two conditions, and the transition occurs when these two are exactly matched. That is, let us estimate where the what is the length scale where the transition occurs. So we have to equate these two, and if you equate these two, you find that the length scale that you get, that's the Jeans length scale, is of the order of Cs divided by square root of g rho, which is the Jeans length scale. So there are essentially two competing processes. One is the process for gravitational collapse, which does not depend on the size, the length scale, it only depends on the density of the object. And the other one is the pressure gradient, the sound, the information that the pressure gradient has to act across that length scale, that information has to propagate that length scale L. That is decided by the sound speed in that medium. So if that information can propagate across this distance before it collapses, then that pressure gradient can act and prevent the collapse. If the time scale for gravitational collapse is shorter, then the object will collapse before the pressure gradient can build up. So this is essentially the crux of the Jeans instability. And Jeans instability, this analysis was first done by Sir James Jeans and it has applications in a variety of situations. So you can apply it to study the formation of structures in the universe. You have this expanding universe, and which is made up of a fluid. You put a perturbation. Question is, will this perturbation grow or not? What we see from this analysis is, yes, the fluctuation does grow provided it's on a length scale larger than the Jeans length scale. If it is smaller than the Jeans length scale, the pressure gradient prevents the growth and you have acoustic oscillations. So that is in the context of the universe. This can also be applied in the context of, say, fragmentation of a gas cloud. I have a gas cloud. In that gas cloud, there are disturbances which could be produced by various other external forces, which the gas cloud will in general be experiencing. And the question arises, is this gas cloud stable or is it unstable? And what this analysis tells us is that it is, if the fluctuation has a length scale smaller than the Jeans length scale, so you have to calculate the length scale for this gas cloud, the Jeans length scale for this gas cloud, and if the fluctuation, the length scale of the fluctuation is smaller than the Jeans, if it is smaller than the Jeans length scale, then these fluctuations do not grow, you produce acoustic oscillations, it's a sound wave. If the fluctuation length scale is larger than the Jeans length scale, then the self-gravity is sufficient to make it collapse. And in this fragmentation process, so there is a certain critical length scale called the Jeans length scale. Length scales larger than that will collapse. And as a result of this collapse, you will form objects of different masses. The smallest mass object that you are going to form is the Jeans mass, whose value we have calculated. I have shown you how to estimate this value. Okay. So this was the Jeans analysis, and I have covered two things in today's lecture. I have showed you how sound waves, how the wave equation, the fluid equations that we have discussed gives rise to sound waves. So if you throw away the gravitational term, the self-gravity, you will only have sound wave solutions, and the sound wave that we have in our atmosphere through which you are listening to me is essentially the same sound wave that we have calculated. The presence of the self-gravitational term gives rise to another effect, the Jeans instability, which is operational for large length scales. So let me stop our discussion of this gravitational instability and Jeans length scale today. Let us stop over here. In the next class, next lecture, we shall resume the same discussion in the context of the expanding universe.